What does the sun sound like? It's a simple enough question, and one that comes with a simple enough answer. The sun is silent, of course. Because sound doesn't travel in a vacuum, to us the sun sounds like nothing at all. But let's do away with simple answers. What if sound actually could propagate through space? Without a giant cosmic muffler between us and our closest star, what would we hear? Would the sun sing to us, an enchanting melody in our sky? Or would its noise be such a cataclysmic cacophony, it would instantly be the last thing we ever heard? Scientists actually have the answer. Through spacecraft like the Parker probe, which is currently making skimming orbits around the sun, they can detect the kind of pressure waves and particles emitted by the sun, and can convert those waves into the sounds we might hear if space was capable of such propagation. And interestingly enough, not all of the sun sounds are the same. Join with me today as we listen to several different sounds made by the sun, recreated through clever science. Because it turns out that these sounds may allow scientists to solve two of the sun's greatest mysteries. In our imaginary scenario, where space has suddenly gained the ability to propagate sound, we can now start listening to the sun all the way from Earth. Although the Earth is 152 million kilometers away from the sun on average, it's perhaps unsurprising to learn that the sun is very loud, easily audible from where we are. It would sound something like this. Just a reminder, there is no sound in space. This is a sound reconstruction, turning amplitudes and frequencies into sound waves, creating clips of what the waves might sound like to the human ear if an atmosphere were present. This soothing buzz has an almost electrical feel to it. It reminds me of generators, or perhaps even something vaguely radioactive, which is appropriate given that this is the sun we're talking about. The nuclear fusion going on inside the sun is equal to 3.85 times 10 to the power 26 watts every second, about 1,000,000 times more than what humanity produces in an entire year. All of this power being created has an unsurprising knock-on effect on the volume of the sound the sun would produce. To get a sense of what this would be like, take the device that you're watching this on and connect it up to the speakers that they use at your next rock concert. Then play this noise at full blast. At 110 decibels, this volume level is survivable for short periods of time, but would likely end up with the entire population of the planet going deaf if they weren't wearing earplugs as it plays in our sky non-stop. In fact, we can consider it extremely fortunate that we don't actually have to deal with this. Species would have probably evolved with no ears, as hearing would be pointless. If we get closer to the surface of the sun, that sound level grows exponentially, with some experts rating it at 270 decibels. Remember, decibels are a logarithmic scale, so every 10 decibels higher it goes, you have to multiply the sound level by 10. To get a sense of how loud this would be, 270 decibels is louder than our atmosphere itself can physically convey. There is a cap on sound at 190 decibels in Earth's atmosphere, as different mediums have different volume caps, due to some complicated quirks of wave amplitude and energy levels, which we won't go into here. The volume of the sun would be 100 million times higher than this cap. The sun is loud, which is a shame, as some of the sun sounds can only be differentiated when we enter that ear-splitting zone. By the time the noise of the sun has reached us, many of the sun sounds have blurred into one, meaning we miss out on some of their fascinating intricacies. To gain a better insight into the sun, we would need to get closer, entering into that blisteringly loud zone of noise. So let's ignore the volume of the sun for now, and instead, let's focus on its sound patterns. If we were to enter a spacecraft and head towards the sun, we would soon begin to hear a difference in the sound's uniformity. Rather than a constant buzzing, we would hear something like this. This is the sound of the solar wind. The sun emits a constant stream of charged particles that blasts out across the solar system, and its existence represents one of the sun's greatest enigmas to date. You see, it's tempting to think of this stream from starting inside the sun and blasting outward under the incredible force of all that nuclear fusion. However, by the 1960s, important discovery had been made through observation. Although particles within the sun's atmosphere, or corona, were moving around with an average speed of 145 meters per second. Particles outside of the corona were traveling at 618 meters per second. This meant that particles that had enough speed to escape from the sun's surface were drifting into space, and then something in the sun's corona was hyper-accelerating them from subsonic to supersonic speeds, firing them off. What kind of process or mechanism is doing this remains a mystery to this day. The corona contains a second enigma too. It is far too hot. Although you might expect the center of the sun to be the warmest part of it, and the temperature to gradually go down the further from the center you go, this stops being true once you enter the corona. The surface of the sun has an average temperature of 5,600 degrees Celsius, but within a few kilometers, the corona suddenly sees the temperature jump to as high as 2 million degrees Celsius. Something in the sun's corona is flicking solar wind into space, and something is making things very hot. Scientists do not know why this is happening either, although it is thought to have something to do with magnetic fields. It is here that we would meet the third sound of our tour of the sun. As our spaceship would draw closer and we passed over the boundary between the corona and empty space, something known in science as the Alton surface, we would begin to hear the following. These are known as linear waves. They are formed by tiny oscillations of plasma particles vibrated by light itself as they stream from the sun through tiny funnels on the sun's surface, and magnetic equivalent to the sound a kettle makes when it boils. We have entered one such stream. Countless of these streams fire out from the sun's surface. The sun's exterior is covered in islands of hot material rising from the star's center. Once there, the material cools and sinks back into the star's mass along the island's edges, and something about this process of rising and falling material, or something going on within the sun itself, makes these sinking zones stream out powerful magnetic field lines. Plasma is scooped out by the magnetic force and is sent streaming into space, the starting point of the solar wind. Just don't know what causes this process, but the sound of linear waves is eerily beautiful. As the winds head out, not all the waves created in this way travel at the same speed. This has the effect of spreading out sounds as faster parts of the wave run ahead, while slower parts of the wave fall behind, creating what are known as dispersive waves. Such waves are filled with chirps, little eddies of sound where fast waves coming from behind meet slow waves already traveling ahead. Eventually, this evens out into the hum we heard at the beginning. There is one last sound that might offer an insight into the entire mystery, one that has some intriguing implications. Here, right within the sun's boiling corona, we can finally begin to detect Whistler mode waves. Whistler waves are the distant echo of high-energy events that ring through the plasma of a celestial body's magnetosphere. We get them on Earth. Whenever lightning cracks, you get more than just thunder. A ripple travels through the planet's magnetosphere that can be picked up kilometers away if you have the right detectors. To truly get a sense of the scale of these waves, here is what they sound like on Earth. Just a few small little cracks and whistles, nothing too special. Now here's what they sound like on the sun. To go from sparse, brief clicks to a cacophony of wailing wind indicates that the sun's magnetosphere is not just experiencing the odd crack of lightning. That is going on constantly, all over, merging individual moments together into one incessant roar. Scientists are still trying to figure out what that roar is being caused by, but at least one theory for the force behind the sound, which can account for the dramatic acceleration and superheating of matter within the corona, is a dry-sounding little event called magnetic reconnection. Electric reconnection sounds fairly innocuous, and yet its innocent technical-sounding name disguises a cataclysm. The sun is a tensely wound-up ball of shifting magnetic field lines, all due to that churning plasma within its heart. I cannot stress enough how powerful these are. When magnetic field lines travel away from the sun, it's sometimes possible for them to merge with other field lines, causing some of those iconic loops to form that you've likely seen in images of the sun before. However, at the moment such arcs are formed, all hell breaks loose. When two parallel lines touch, creating an arc is a massive realignment in the excess field line's polarity. Everything above the arc needs to find a place to go to ensure magnetic equilibrium is maintained. Cut from their tethers, the field lines further out from the sun form an arc of their own, which then catapults off into space, like the releasing of a gargantuan stretch rubber band. This rapidly accelerating magnetic force is known as a nanoflare, and it indirectly heats the corona above it to multi-millions of degrees in seconds. Scientists have only recently developed the capability to be able to even see nanoflares, and aren't entirely certain the nanoflares they've seen are indeed the hypothesized events they were expecting, although they do seem to be accompanied by the expected superheating. This is an explanation that is still being worked out. Most of it is not yet understood. And still, it's not completely far-fetched that such moments when the sun gets so wound up it snaps. Explain why its corona is as hot as it is, and why it is flinging solar winds out across the solar system, with quite the force we witness. Although to go from a single crack into the roaring wail that we hear, and to account for the constant solar wind traveling outwards in all directions from the sun, nanoflares, or whatever the force behind this phenomenon is, must be extremely widespread throughout the entire corona. This is it for today's video. What do you think of our video? Feel free to share your thoughts in the comment section below. Don't forget to like and subscribe to our channel for more future updates. Thanks for watching.